In lesson 6.1, we're going to be talking about vectors. A vector quantity is something that has both direction and magnitude. Another word for magnitude would be the size. For example, velocity. When you're traveling, it is important to know in what direction you're traveling and how fast you're moving. So that would be a vector quantity. A quantity that has no direction is called a scalar quantity. That has no direction. So that's just a magnitude or a size. We use directed line segments to represent vector quantities. So you can see here, this is an example of a vector where we've got an initial point P, we've got a terminal point Q, and you see there's an arrow on the end of that, so that's a directed line segment. It's pointing in the direction that it's traveling. And then we're going to, it's labeling it there with notation, PQ, with a an arrow on top. So we can see that all these arrows are going in the same direction, so that's how we're showing the direction here. The length of those line segments will represent the magnitude. The length of each line segment will represent the magnitude. So if it's a smaller line, it's got small magnitude, and if it's a long line, it's got a large magnitude. So a vector is a directed line segment. A vector is a directed line segment. Two vectors are equal if and only if they have the same magnitude and same direction. They must be the same size and they must be going in the same direction for them to be equal. The magnitude or length of a vector can be found using the distance formula. And the notation for that is going to be what you see right there, which is a double bar around vector PQ. So to do that, remember the distance formula is the square root of x2 minus x1 squared plus y2 minus y1, all squared. In example 1, let vector u be represented by the directed line segment from 0, 0 to 3, 2, and vector v be represented by the directed line segment from r1, 2 to s4, 4. Sketch a graph of each vector and show that u equals v. So the graph is going to show us that the directions are the same. We're also going to see that the lines look to be the same magnitude, but we're going to use distance formula to check that. So the first one goes from 0, 0 to 3, 2. We're going to plot that. 0, 0, 3, 2 is the first vector. I'm going to label that P and Q. And then the next one starts at 1, 2. Starts at 1, 2 and goes to 4, 4. So we can see they look to be about the same size. That is R and S, and they look parallel. They are pointing in the same direction. Now to show that they have the same magnitude, we're going to do distance formula for those. So the distance of PQ is equal to, we have x2 is 3, minus x1 is 0 squared. We have y2 is 2 minus y1 is 0 squared. And I'm getting that from these x's and y's up here. And when you do that, you're going to get square root of 9 plus 4, which is square root of 13. So that's the magnitude of vector PQ. We're going to do the same thing for our S. So we're going to have 4 minus 1 squared plus 4 minus 2 squared, which also gives you radical 13. So we have shown that they're going in the same direction, and they have the same magnitude. And so we have shown that vector u is equal to vector v. Now we're going to talk about component form of a vector. The component form of a vector with initial point p1, p2 that terminates at q1, q2 is going to be given by this, where you subtract q1 and p1, that's going to be your first component, and then q2 and p2 is going to be your second component. And so you'll write it with this notation here. And then the magnitude, this is how we found it using distance formula. This is how you would find it using component form. If you end up getting 1, then it's called a unit vector. If you get a magnitude of 0, then it would be the vector 0. Find the component form and magnitude of vector u that has initial point 4, -7, and terminal point -1, 5. So here what we've got is a P1 and a P2, and we've got a Q1 and a Q2. So if you use this equation up here, we can put it in component form. So vector u, which is bolded and has an arrow on top, would be Q1, which is -1, minus P1, which is 4, comma Q2, which is 5, minus P2, which is -7. And then here we're getting -5 and 12. So that's the component form. Now we could use distance formula again like we did before, or we can use our component form. So the magnitude of vector u is equal to, and now I'm going to look at that component form equation, which would be the square root of v1, which is -5 squared, plus v2, which is 12 squared. And then when you do that, you get the square root of 169, which is 13. So you've got your component form, and then you've got your magnitude. The product of a vector v and a scalar k is the vector that is absolute value k times as long as v. As long as vector v. If k is positive, then k times vector v has the same direction as v. And if k is negative, k times vector v will have the opposite direction as vector v. We can see this in the examples over here. So we've got a vector v. Then you're seeing that this is half the size, and you see that there's that 1/2 in front, the scalar 1/2. Here you can see it's double the yellow size. That's what the 2 is doing. Here you're seeing the arrow is pointing in the opposite direction because we put a negative scalar in front. And here it's in the opposite direction, and it's 1.5 times as long because of the negative and because of the 3 halves. The sum of vector u plus vector v is formed by joining the initial point of the second vector with the terminal point of the first vector. So there's a picture here that shows that vector u, and then we've got vector v. You can see that we're leaving u where it is. Then we're taking vector v, and we're attaching the initial point of vector v to the terminal point of vector u. And wherever u starts and v ends, that's the new vector, u plus v, which we're calling the resultant. This is called the resultant of the vector addition. You've got some properties up here. If you're adding vectors, you just add their components. the components of u and v together. If you're multiplying by a scalar, you multiply each component by that scalar. And then you've got some different rules here for operations with scalars, with addition and multiplication. So with vectors and scalars. So example 3, we've got vector -2, 5 and vector w, 3, 4. We're going to find and sketch each of the following vectors. So by hand, we have a scalar 2 times vector v, which we're just going to multiply each component by 2. And we can draw a sketch of that. If we take the initial vector, let's sketch that. With the vector component, we can just assume that it's starting from 0. So starting from 0, we're going -2 in the x direction and +5 in the y direction. So that's your original. Then when you multiply it by 2, you see that it's twice as long. So you're -4 in the x direction, and you are, oh, I got that wrong. So sorry, that is a 10. And then you're 10 in the y direction. And you can see that they overlap if your graph is good, and it's double the length of that red vector, which is what the 2 is doing. Let's subtract vectors now. So we've got w is 3, 4, minus vector v is -2, 5. And to subtract them, you're taking vector w, and then you are subtracting the components in vector v. And same thing for the y component. So you've got 4 minus the 5 from vector v, which is giving us a resultant vector of 5 and -1. And then let's graph that. All right, so my original 2, let's graph those. We've got 3, 4. And then we've got -2, 5. And we're adding them together, and we get 5, -1. And why would we get that green? So we're starting with w, so that means we're leaving the 3, 4 alone. We're leaving that blue alone. And then we're taking the red one, and we are subtracting it. So we're taking the red vector, and we are moving it over here. So I'm putting the initial point of the red vector at the terminal point of the blue vector, and we've changed its direction. It's now pointing in the opposite direction because we were subtracting. That's how you can see how the green vector was created. C, you're going to take vector v, which is -2, 5, and add 2 times vector w, which is 3, 4. First thing I did was multiply the 2 by the 3 and the 4 to get 6, 8.